Good morning once again. So after the tea break, in this session, we have with us Dr. Sanjeev Kumar, who is professor in mechanical engineering in PEC University of Technology. Dr. Sanjeev has a very long and rich experience in industry and teaching. So he will discuss with you process optimization by Taguchi experimental design. So I request Dr. Sanjeev Kumar to please start.
Thank you. So, good morning, everyone. Am I audible? Okay, clearly here. Okay. So, we are going to talk on process optimization by Taguchi experimental design. Normally, we have many softwares available by which you can do this Taguchi analysis. You give input, you get graphs, everything. But here the treatment which I am going to give is purely conceptual in nature. So we will take up this, the analysis, how Taguchi analysis is done. What are the requirements, what do we want to achieve, and how do we achieve all that. So I will start with an example. Suppose you are conducting an experiment. Obviously, you desire some output. You desire an optimum output. What do we mean by optimum is that given the different input parameters, what combination of those input parameters would give you the best result? Obviously, you are interested in the best result. Okay. Not only that, we need to know what is the effect of the parameters, because there will be a relative effect of the various parameters. It could be a machining process. It could be a you may be designing an electrical circuit. Okay, you may be doing some cost analysis. So in each case, you have a definite defined output. You want to, suppose you are doing cost analysis, you want to keep the cost minimum, isn't it? You are doing a machining operation, since most of you are from the mechanical engineering background. We need to maximize the material removal rate, isn't it? So this way, there can be so many different examples. In fact, Taguchi is not limited to only mechanical engineering or manufacturing or conducting experiments. So maybe if you are not aware, it would be interesting to know that this method was first evolved to maximize the agricultural yield of a farm. Okay, so obviously, like in that case, there would be inputs like the quality of seed, isn't it? The kind of fertilizer we are giving, the kind of water available, all those things were there. So taking all those into consideration, we are trying to maximize the yield. And the output of my farm should be maximum. That is my aim, and of course, without sacrificing the quality, isn't it? So, and in fact, you will find that when we go into the details, many terms of this Taguchi method have actually come from the that background. So we have terms like treatment. Okay, so those things are there. And then once we have, so right till now I have covered two things. One is that whatever is the response or whatever is the output, we want to optimize it. It could be maximize, it could be minimize. Like minimize, I gave you example of cost, isn't it? Then we need to know the effect of various parameters. Like just now I have talked of seed quality, I talked of a fertilizer, I talked of the water availability for that crop, isn't it? So we need, as an experimenter, we need to know which out of these is more affecting my yield, isn't it? So that I am able to concentrate on that, isn't it? So this method will give me the relative importance of the various parameters that I have taken into consideration. Not only that, I need to know, because each parameter will have different levels, isn't it? Like seed quality, maybe 3 qualities will be available in the market. Fertilizer, maybe 3 types of fertilizers, or you are combining 2 fertilizers in a given percentage, like that. So what is the relative effect of all these on my output? So all these you are able to get by this method. So let us now go into the detail of this. First, these are some general slides. I'll just go through them quickly. So as you can see, so I have prepared a list of optimization techniques, various optimization techniques. You know all of them, most of them you know, isn't it? You know the classification also. We have mathematical techniques. I can see from that you have studied linear programming, non-linear programming, all that, multi-objective programming, all that you have covered. Then we have stochastic techniques. Stochastic techniques, we mean mainly by stochastic technique where the role of different parameters is highly uncertain. Like in a machining operation, the role of various parameters is highly uncertain, where we cannot quantify, or we cannot, it is very difficult to give a value to the parameter we have selected. There we call them as stochastic techniques. And third one, of course, we have statistical methods, in which we have regression analysis, very common. Most of you are familiar with it. We have design of experiment, discriminant analysis. So we will be covering on this one, design of experiments. When we talk of optimization, of course, lot of it must have been talked about already. So it is not only limited to mechanical engineering. You use it for finding the optimum trajectories of space vehicles. You use it for civil engineering structure optimizations. You use it for machining conditions. You even use it for optimum design of electrical networks. Coming back to a more business-like, shortest route to be taken by a salesman who is visiting different cities. So that is also a kind of optimization activity, isn't it? Then of course, design of material handling, design of optimum pipeline networks for process industries. So this is a very, of course, it is not all inclusive. This is a general idea of where all you will find the applications of optimization. Coming to process optimization. So this slide mainly consolidates what I have talked to you till now. So let us go through it. This is very important. Process optimization can be defined as the method of finding the conditions that will give the maximum or minimum value of a response. Okay, is it clear? To determine the controllable factors that will affect the desired response, isn't it? To minimize the effect of uncontrollable or noise factors. So I'm sure it has been discussed, controllable and uncontrollable factors, noise factors. I will also briefly touch on this. Next, to determine the optimum combination of controllable factors that will give the best value of the desired response. For this next point we have not covered till now, multi-response optimization, where a balance is to be achieved between a number of desired responses. Because any process you see, when you try to optimize a particular parameter, particular response, the input parameters, different parameters will have different kind of effect on that response. Increasing a parameter may reduce that response. Reducing a parameter may increase that response, like that. So what we need to do is we need to have a multi-response optimization where a combination of all those factors is reached. And lastly, two of the most commonly used techniques for process optimization are Taguchi experimental design and response surface methodology. Both these methods are very commonly used in our research work, maybe at MTech level, maybe at PhD level. So here I have given an idea of examples of controllable and noise factors. Any process will have controllable factors and uncontrollable factors. Like some examples are there. If we talk of controllable factors, design parameters, of course, dimensions, material selection, you can do that, isn't it? Process design, process setting parameters, all those are my controllable factors. Some example, we'll not go into all these details, but just to give you an idea, noise factor, piece-to-piece variation. Even like if I take another example from the mechanical engineering background, you are carrying out a machining operation, maybe a turning operation with the help of a tool. Now, as the process is being carried out, tool is veering, isn't it? The quality of the tool or the maybe sharpness or angle, whatever, nose radius, whatever we may call it, at the beginning of the cut is not the same as at the end of the cut. So this is a uncontrollable factor, or we call it a noise factor, isn't it? Parameters like temperature, humidity, they will also not remain same throughout the experiment. And we have no control over them, isn't it? So this is again an example of uncontrollable or noise factor. Now, when we conduct an experiment, of course, there are different strategies. Best guess experiment. What do we mean by this? By intuition, we know certain things, isn't it? Like if I increase the feed rate, material removal rate will be increasing. So this I know by intuition. So by using my intuition, by using my inherent judgment, I can make some planning for my experiment. I know by intuition that certain factors are not significant, or maybe certain factors are more significant than others. Okay. So that is my best guess experiment. One factor at a time, again, is very simple. There are so many parameters. You vary one parameter at a time, isn't it? Keep on doing it. You will get so many results. Your experiment will be conducted fine, but the problem is it will take too much of time. It will take too much of resources. Okay. And it will not result in that much improvement in the quality of the response. Okay. And obviously it is devastated by interaction. What do we mean by interaction? Is we are changing one parameter, but its impact with respect to another constant parameter that also changes. That is meant by the interaction effect. And lastly, we have statistically designed experiments, which are based on, basically they are all so many different kinds of experiments we are conducting. They are all based on the Fisher's factorial concept. In fact, the Taguchi methodology is also based on the theory initially propounded by Fisher. So when we come to the experimental design, I'm right now talking of only the experimental design. We can have full factorial design in which we take all possible combinations into effect. Fractional factorial, we reduce those number of combinations in such a way that the effect on the output is not there. We try to minimize that effect, but maybe if there's a marginal effect, it is acceptable because we are reducing lot of time, lot of efforts we are reducing. If orthogonality is maintained, the fractional factorial matrices would be called as orthogonal arrays. So this I will visit further. We will be talking about this in detail because the Taguchi methodology is based on the application of orthogonal arrays. I will put it on screen, and one handout is also given to you. So which is an example of orthogonal array. When I talk of that array, when we talk of the orthogonality, that will be useful to you. We also, this I just wanted to touch because we are dealing with Taguchi method. We call Taguchi method robust experimental design. So I just wanted to emphasize, why do we call it robust? Okay. The fundamental principle of robust design is to improve the quality of a product by minimizing the effect of the causes of variation without eliminating these causes. So we are not eliminating the causes. We cannot eliminate the causes. As already pointed out, the causes we cannot eliminate. Only thing is that we have to minimize the effect. So that is the fundamental principle of robust design. This is achieved by optimizing the product and process designs to make the performance minimally sensitive to the various causes of variation. This is known as parameter design. Parameter design we will cover. Okay, the next one is not that important. Next, I'll come to the robust design methodology serves as an amplifier. That is, it enables an engineer to generate required information needed for decision making with much less experimental effort. So what we need to do in the robust design is we have to achieve two important tasks. Establish a leading indicator of quality. What is the response I want? That of course the experimenter has to decide. What is the response? Whether I am interested in agricultural yield, whether I am interested in the quality of the crop. I'm not interested in to maximize my yield. That may be my motive, but I am interested in quality. I want the best quality. Similarly, when I am doing the cost analysis, maybe I am not looking for minimizing the cost. I am looking for maximizing the production. So that is my only aim. That could be one. So this will be decided by the experimenter. You can have one response, you can have two responses, you can have multiple responses. Second point is obtain reliable information about the process parameters with minimum time and resources. This will be achieved by employing signal to noise ratios to measure quality and orthogonal arrays to study the many design parameters simultaneously. So when we will talk of our method in detail, we will again and again be talking of signal to noise ratio and orthogonal arrays. The application, as you will see, the applications of robust design are not limited to the engineering field. The technique has been successfully employed for profit planning and even cash flow optimization. Lastly, robust design methodology offers simultaneous improvement of product quality, performance, cost, and engineering productivity. one or two things I want to emphasize. In the statistical experimental design, in a normal experimental design, noise factors are either kept at constant values or we use some techniques. These techniques are available. Blocking and randomization are employed to minimize the effects of noise factors. Whereas the fundamental idea of robust design is to find those level of the control factors which minimize the sensitivity of the product function to the noise factors. The statistical experimental design is more useful for continuous factors. This again is very important. So we can use statistical experimental design only when we have continuous factors. It gives much better results. But orthogonal arrays you can use for continuous as well as discrete factors. I hope you understand the difference between continuous and discrete factors. Lastly, in statistical experimental design, presence of interactions among the model factors is not viewed as highly undesirable. So that means even if some interactions are there, we tend to ignore those interactions in a normal design. But in robust design, we eliminate the effect of interactions. Again, by using the orthogonal arrays and proper assignment of the columns. So now I begin with my proper methodology. With this background, I begin with the steps in the Taguchi methodology. So what we have is, I will go through them now, then we will take them up one by one. First is decide the important input process parameters and their levels. So what we have to decide is, what are the input process parameters for my experiment? There may be like, okay, I will give an example. Later on I have covered it, but I'll just touch upon it. So I have taken a process here as an example. So it is obvious, most of the things are better understood with the help of an example. Otherwise it becomes very boring. So what we have here is, we have these process parameters. This is a total list I have prepared. So that is the role of the experimenter or the researcher. When you plan to conduct an experiment, you will first list down all the process parameters that you are likely to encounter in your experiment. So we have here discharge current, sparking voltage, type of flushing, type of dielectric, pulse on time, pulse off time, polarity. Okay. Now you have to decide out of these which factors are more likely to affect my process. Maybe you eliminate 1, 2, or 3 out of them straight away. Either through literature survey, we all have been doing literature survey, either through literature survey or by conducting pilot experimentation. You conduct a pilot experiment, suppose, let me give you an example. You want to find out whether my voltage is affecting my process or not. You are carrying out a machining process. You keep all other factors constant. Take voltage as 30 volts. Find out your material removal rate or whatever is your response parameter. Change it to 40 volts. See the difference. If it is not significant, of course, this parameter is not important. Much of this information is available in the literature. You can also conduct pilot experimentation to find out. Okay. I again come back to the first step. decide the important input process parameters and their levels. What do we mean by levels? Again, I come to the same example. Suppose the machine on which I am conducting my experiment can give me a voltage range of 30 to 120 volts. That would be the, maybe any machine would have a definite capability, 30 volt to 120 volts. Steps may also be defined. It may be a continuous variation. By continuous variation, I mean that you can set it at 36 volts also, you can set it at 42 volts also. But it may be a discrete variation. Normally voltage has discrete variation. That means you can set it at 30 volts, 35 volts, 40 volts, 45, nothing in between. Okay. So what level? But the type of response you have selected, which is the level range in which it is getting most affected, that you have to decide. So again, you can do it by pilot experimentation or literature survey. Maybe you find out that from 60 to 90, the lower range of voltage is also not very important for me. The highest range of voltage is also not very important for me. I am interested in, say, 60 to 90 volts. Now within that 60 to 90 volts, which levels I need to study? Will my experiment require 60, 65, 70, 75, 80? Or I will be able to get my inference by 60, 70, 80, 90. That again the experimenter has to decide. So that is what we mean by here levels. Then we come to the response parameter. Response parameter, as I have already mentioned, what is the response parameter? I want highest material removal rate, or I want best surface finish. What is the response I want? And its characteristic. By characteristic, I mean that I want to maximize it or I want to minimize it. Okay. Then select the appropriate orthogonal array and assign the parameters to its various columns. Now here I will again go to a, now these are two examples of orthogonal arrays. Now this require a, if you are not familiar with it, this requires a little bit of understanding. Let me concentrate on this L9. L9 you can see, L9 orthogonal array. The one which I have given you is L18. Okay. L9 orthogonal array, it consists of rows and columns. Okay. There are some numbers. At present, they just seem 1, 2, 3. But let us see what they mean. Each column corresponds to one of the factors. And each row corresponds to the value of the input process parameters at which that experiment is to be conducted. Okay. For example, I have taken very simple, let me take two terms which we are familiar, voltage and current. I have kept voltage at 3 levels, 60, 70, 80. I have kept current at 3 levels, 10 ampere, 15 ampere, 20 amperes. Now I will assign each factor to one of the columns. So suppose I assign voltage to first column. What do I mean at 1? 1 means 60 volts. 2 means 70 volts. 3 means 80 volts. I assign the current to column number 2. 1 means 10 ampere. 2 means 15 ampere, 3 means 20 ampere. So I think you can guess now that this L9 orthogonal array I can use to study 4 factors maximum. Got it? Is it clear to everyone? Is it clear? Okay. So columns I have explained. Now we come to row. Now for each row corresponds to one experiment. That means first experiment I will conduct at 30 volts and 10 amperes. Second experiment I will conduct at 30 volts and 15 amperes. Third experiment I will conduct at 60 volts and 20 amperes. What about the fourth experiment? 70 volts and 10 amperes. Similarly, the values of other parameters will be taken. Now, I will emphasize the beauty of this method. If you have 4 factors, each has 3 levels. If you want to conduct the complete experimentation, you need to conduct how many? 3 raised to power 4, 81 experiments. In this method, you get the complete information just by conducting 9 experiments. So just appreciate the effort in time and resources that you have saved. Okay. So there are total standard 18 orthogonal arrays, because depending on your experiment, you could have so many different factors. You could have so many different levels. You may decide that I have 7 factors. My levels are 6 levels each. Maybe, no problem. We have a standard orthogonal array for that. Depending on the number of factors and the number of levels, you will select the orthogonal array. So you have understood? In software, this is done automatically. So you don't come to know. You just give your number of factors, you give your number of levels, it decides the array. Okay. Now I come back to, so select the appropriate orthogonal array and assign the parameters to its various columns. Like we assigned voltage to the first column, current to the second column. This assignment is very important. You cannot do it at random. Usually the factor which you think is going to be most significant is assigned to the left side, usually. Or a factor in which changing level from 1 to 2 is very difficult, you assign to the left side. This comes with a little bit of practice, of course. Immediately that will not come, and that is not my intention also. The intention is to right now to just give you an idea and scope of this method. Third point. Yes.
Sir, just now you showed that orthogonal array for 9 experiments, 4 factors.
4 factors.
And if my factors are more,
Yes.
and levels are, let us say, 3.
Yes.
That means, whether I will be able to use L9 orthogonal array, or I will have to go for something else.
You have.
On what basis I will decide?
Okay, you have more number of factors. Obviously, this array cannot accommodate more than 4 factors, isn't it? So you have to go for a higher array. Again, you may be having 3 levels. Like suppose you have, say, 7 factors of 3 levels. Then you can go in for L18, which I have given there. So you can just see that So you conduct 18 experiments and you get your results. But it may be possible that you have number of levels different, maybe 5 levels, 6 levels. Then you will have to go in for some other array. So that selection of orthogonal array, as I told you, and the assignment of columns, factors to the columns, is very, very important. Okay.
What is the base for coming out for this particular orthogonal array?
What is the
Basis, on what basis we are claiming that this particular orthogonal array is likely to give me?
It will suit me. Yes. So
Statistical basis.
yeah, it is statistical base. One thing is that it must be able to accommodate the number of factors and the number of levels that you desire. That is the first requirement. Second thing, I gave you 2 reasons to, these are general indications that you assign those factors to the left side which are more important or whose levels are difficult to change. Okay. There is another very interesting thing. At the end, it will calculate the percentage error of your experimentation. The method will calculate, we will come to that, but you have raised the question, so I am giving that clarification right now. It will calculate the percentage error of my experimentation. A thumb rule is, if that percentage error comes more than 5%, that means your experiment is to be rejected. That means either your array selection or your assignment of columns was not optimal. Lower the error, better it is. Got it? Coming to the third point. This I have already explained. Conduct experiment for the levels given in each row randomly. Okay. So maybe you will take a first row, third row, fifth row. Don't do it in a continuous way. And note down the values of the response parameter. Of course, once you conduct the experiment, you know the response parameter value. You note it down. Repeat each experiment 3 times. So repeat each experiment 3 times. Next point is study factor effects and find out the optimum combination of input parameters. Once you know the value of your response parameter, then my analysis part starts. I will study the factor effect, how each factor and each level change in a factor is affecting my response. So I will be able to get that through my analysis. And then it will give me the optimum combination of input parameters. Calculate the best value of the response characteristic. We will come to that. Next point is calculate the range within which experimental value should lie and conduct confirmation experiment if required to verify the same. Okay, this I will explain. Again, though L9 is a very simple array, but given the time constraint and the general nature of our talk, this would suffice. Now I have conducted 9 experiments. I used 4 factors. I have conducted 9 experiments. Obviously, you will appreciate that this array does not contain all the possible combinations, because all the possible combinations are 81. It contains only 9. It is possible that once I found out my optimum combination of parameters, please concentrate on this. This is very important. That particular combination may be existing here as one of the rows, or it may not be existing. There's a possibility. If it exists here, I have already conducted experiment on those values. But if I have not, I need to conduct an experiment on those values which I have obtained as a result of my Taguchi analysis. And you see the beauty. Before conducting that experiment, its analysis will tell you that by using that combination, how much output you are going to get. Okay, I'll show you how. I'll show you how. So this is what we mean by here. Now I have, to some extent, I have explained. Calculate the best value of response characteristics. Calculate the range within which experimental value should lie, and conduct confirmation experiment. So this is what I mean by confirmation experiment. Perform analysis of variance to find out the significance of various factors and their relative contribution. So I will perform that ANOVA analysis and it will tell me. In fact, what will happen is, now here I have only 4 factors. Now suppose you were talking of 7 factors. Though by your judgment and by your pilot experimentation, you found that a certain factor was significant and you used it in the orthogonal array. But actually it may not be significant. That is based mainly on your judgment. So this analysis will tell you whether the 7 factors you have taken are all significant or 1 or 2 of them are not significant. It will tell you, and it will also tell you their relative contribution. If you take a contribution of 100%, how much each of the factor is contributing. Exact quantitative value it will give you. Okay. So now we will go into the detail one by one. Some definitions, I will quickly run through them. You will not remember them also, and from the conceptual point they are not very important also, but still designed experiments, they are called matrix experiments, and each individual experiment is known as run or treatment. Okay. Settings are referred to as levels and parameters as factors. Response variable is a dependent variable, that of course we all know. The input parameters, input variables are independent variables. Independent variables. So that is why factors are also called independent variables. Factors are also commonly known as treatments, a term which comes from agriculture, where design of experiments was first developed, like I told you. Another term is degrees of freedom. This we need to understand. Like in our case, suppose I have a 3-level factor. Like I have taken 60 volt, 70 volt, 80 volt. What will be the degree of freedom of this factor? You will start with any value at random out of these 60, 70, 80. Maybe you took 70. That becomes your initial value. From 70 volt, it can go to 60 volt and it can also go to 80 volt. So the degree of freedom is 2. Degree of freedom is 2. So for each factor, the degree of freedom is number of levels minus 1. Columns of the array are mutually orthogonal. Okay. What do we mean by this orthogonality? It is explained here. You can check it with your the sheet I have given you also. See, it means that for any pair of columns, so you have so many pairs, you have so many columns, you have all combination of factor levels occur and they occur equal number of times. You can check it. Maybe you can take 1 and 2, not right now. Maybe 1 or 2 you can take, then you can take 1 and 8. You will find that all combinations occur and they occur equal number of times. That is why they are known as orthogonal arrays. Okay. Rest I have covered. I come to the second last point. Taguchi has tabulated 18 basic orthogonal arrays. So preferably they are to be used. They are known as standard orthogonal arrays. But it is generally possible to select one of these for a specific requirement. But you can modify these arrays also. Suppose your requirement is such, you can modify them. This I have shown you. First, I will cover that point, how we can modify them. There are 3 techniques available to modify the standard orthogonal arrays. First is the dummy level technique. I will explain this in detail later on if we have time. It allows a factor with m levels to be assigned to a column of n levels where n is greater than m. Okay. So what do I mean here? That you can assign a 2-level factor to a 3-level column. There is a method available for that. You can assign a 4-level factor to a 6-level column. You can do that. Column merging method. You can be used to create a 4-level column in a standard orthogonal array of all 2-level columns. What do I mean here is that in a given experiment, you talked of 7 factors at 3 levels, but that may not be the requirement. Out of those 7, you may have 5 3 levels and 2 maybe 6 levels. It may be the requirement. You need to study it. It is the requirement of your experiment. So you can modify by this column merging method. You can modify a standard orthogonal array. So what you can do is, an example we have given, a 9-level column in a standard orthogonal array with all 3-level columns. So with all 3-level columns, we can put a 9-level column, 9-level factor also in that. So that is the column merging method. And lastly, we have the compound factor method. It allows the study of more factors with an orthogonal array than the number of columns in that array. But this method is better avoided. You better go in for a higher order standard orthogonal array, because this needs a number of calculations. Unless until you have thorough knowledge of this method, it may lead to error in results. Okay. So these now, so these are some of the standard, some idea about the standard. Like if you have 2-level factors, for 2 to 3 factors, you can use an L4 orthogonal array. 4 to 7, you can use an L8. 8 to 11, L12. 12 to 15, L16. 3 levels, 2 to 4, you can use L9. 5 to 7, you can use L27. Then there are mixed arrays available, L18, L36, L50. In these, what do we mean by mixed array? Different columns, even in the standard array, have different levels. So that is a mixed array. 5 levels, even 5 levels. Number of factors 6, you can use an L25. Number of factors 11, you can use L50. This I have already covered. So now, whatever steps we discussed in that previous slide, one by one with the help of an example, I will take up. Very simple example I have taken, so as you get the basic understanding of the method. So these were my, suppose I want to conduct an experiment. These were my, all the possible process parameters. So out of these, I have selected 3. Out of these, I have selected 3 based on my pilot experimentation, based on my literature survey, and their levels also. That is to be decided by the experimenter. Now what I have done is, 3 levels of discharge current I have taken, 2 ampere, 4 ampere, 6 amperes. 3 levels of pulse on time. This is just an illustration. 5, 10, and 20 microseconds. 3 levels of pulse off time, 38, 57, 85 microseconds. This I have done. And before that, okay, response will come later on. Now I have 3 factors of 3 levels. So I know by my judgment that L9 will be able, I will be able to easily conduct my experiment with L9. Otherwise, I select some other array depending on my requirement. Now the response characteristics, I have taken 2. After conducting this machining operation, I have taken hardness as one of the hardness of the machined surface. So obviously, higher the better. Higher the better. I have taken this as the, now this is the my characteristic of my response parameter. Higher the better. I have taken second one, I have taken surface roughness. So deliberately I have taken 2 such responses, one of which is higher the better, other one is lower the better. Surface roughness I want minimum, isn't it? So based on these inputs, L9 orthogonal array was selected and 4th column of the array was left blank. So you cannot overlook an row. Every row is to be taken into consideration, but columns you can miss. So you put 3 factors, 4th column is left blank. That will not affect your experiment because all columns are orthogonal in nature, isn't it? All combinations occur equal number of times. So if you leave a column, doesn't matter. So you can always use an orthogonal array with 9 columns to study 6 factors. You can always do that. Okay. Orthogonality of an array is not lost if 1 or more columns are not used. Each row of the orthogonal array represents the set of values of input process parameters with which a particular experiment is to be conducted. This we have already emphasized. So a total of 9 experiments are required for the complete study. Also, Taguchi strongly recommends that rows must be selected randomly and each run be repeated 3 times. So this is the after C. Now this is making things more clear as I explained earlier. So first column I have assigned a discharge current. Second column I have assigned pulse on time. Third pulse off time. So the levels I have fixed, I have written here, isn't it? Now I have to conduct all these 9 experiments. Once again I repeat, suppose I conduct 6th experiment, I will take the values 4 ampere current, 20 microsecond pulse on time and 38 microsecond pulse off time. All the values are known to me. I will conduct the experiment. Is it clear? I think we need to go a little bit faster. Compute. Now after that,
Hello.
hello. Question? Yes.
Hello. Yes. It is Srinivasa from Marga Digital Engineering.
Yes.
Yes. I have query on this. While selecting the parameter for pulse of time, you have considered 3 levels. That is, first one is 38, second one is 57, third one is 85.
Yes.
Is that it? How it is possible to take the 3 levels?
Pardon?
Pardon? Actually, pulse of time, you have considered the 3 levels. First one is 38, second one is 57, third one 85. On
Yes.
what basis you have selected the 3 levels?
Okay. On what basis? Yes. I have already explained. See, what happens is it is governed by the two things. One is the requirement of your experiment, which you will decide. And second is the availability of those values on the machine, because you will conduct that experiment on a machine, isn't it? So the values it is having, as I told you, it could have a continuous function, it could have a discrete function. So the one I am talking of is a machine which is giving me discrete values of pulse of time. So overall, maybe, okay, as I told you, this is an illustration. Maybe pulse of time is available to me from 20 microsecond to 1000 microsecond. Now this is a very, very long range. Depending on my judgment, depending on the response characteristics that I have selected, I will choose a given range within which I have to conduct my experiment. Now within that range, now what are the levels? Suppose I decided that from 30 to 100 microsecond will be the requirement of my experiment. Given my my research area or my response characteristic, I don't need to go below 30 microsecond. I don't need to go above 100 microsecond. Now within that, the machine allows me to choose, it is a discrete function, 38 microsecond, 57 microsecond and 85 microsecond. So that is how I have selected them. I hope it is clear. We'll continue.
Hello. The fundamental rule in selecting the parameter. The fundamental rule in selecting the parameters is, once you select the parameters, the gap between first level, second level, and second and third level must be same. But here that is not same.
Not
that must be fundamental. For example, you can take the first factor, sir.
Yes.
Please go to that table what you show me online.
Okay.
Can you hear me?
Yes.
In this first factor, they are selected as 2, 4, 6. The difference between first level and second level is 2, and second and third level is 2. Again, you can go to the second factor. What are those values? I am not getting there. The difference between first and second level is same, but second and third level is same. Whereas coming to the third factor, it is not coinciding. First and second level is 19, second and third level is 28. It is acceptable.
Okay, let me when we talk of the third factor, first level has to come in the first experiment, second level has to be come in the second experiment, third level in the third experiment, then in the fourth experiment second level has to come. So we'll just cross check we have given it this way or not. 2, 3, yeah, we have given it rightly. So you see fourth experiment, we have given the second level, which is 57 microsecond. And then the third level, which is 85 microsecond. Then the first level. You now cross check with this.
No, what I am saying is, you have taken for third pulse of time, 38, 57, 85 are the 3 levels.
Yes.
The difference between first and second level is 19. Usually, the difference between first and second level is 19, whereas second and third level is 28. Is it really possible to conduct experiments in that manner?
Okay, we'll do one thing. Let me continue. We'll take it up at the end. Okay, we'll take it up at the end. So this I have taken. Now these are the values. Like I said that we have noted down the value for each micro hardness as well as surface roughness. So for each experiment, I have 3 values which I have taken over here. Okay. Then what I need to do is I need to calculate the signal to noise ratio. Okay. For this, the formula is here I have given. So signal to noise ratio for larger the better. You can see this formula. So summation of 1 upon yi square, where y is the value of the raw data, y1, y2, y3 we will take, summation 1 upon n, that is 1 by 3, and then we will take the log value, multiply it by minus 10. For smaller the better, the yi square comes in the numerator. So that is the difference. What difference it is ultimately going to make is that though the response characteristics is seeking the minimum value. You remember for the second one, surface roughness, we had taken the minimum the best, minimum the better. So my response characteristic is seeking the minimum value, but my SN ratio will still seek the highest value because of this change in formula. So my SN ratio will always seek the highest value. So that means that I am suppressing the noise and maximizing the effect of controllable factors. That is what I mean by SN ratio. Okay, so I have calculated, so just go through this. We have calculated SN ratio for separate SN ratio for each experiment for hardness and SN ratio for the surface roughness. We have calculated all these values and we have calculated the mean also because we will be using them subsequently. Okay. Now, what I need to calculate first thing, if you recall when we were discussing those steps in the Taguchi methodology, now we will quantify the effect of each factor at each level. So this is very simple. How we do it? Suppose, okay, let me not take the first one. Effect of factor A at level 2. Effect of factor A at level 2. What were the rows in which factor A was at level 2? Take the average of that. So 4th row, 5th row and 6th row. So if you go back, okay, I will go back and then explain. Suppose I want to calculate the effect of third factor at level 2. Third factor at level 2. Which all rows I will take? 2nd row, 4th row and 9th row. Is it clear? I will repeat it. I will repeat it. Suppose I want to study the effect of second factor at level 3. Second factor at level 3. I will take row 3, row 6 and row 9. So what you get here is that we are segregating all the effects. Within those 9 experiments, we are able to segregate all the effects, isn't it? Now I am consolidating it. These are the effects. So peak current at level 1, peak current at level 2, peak current at level 3. Here it will not mean much to you. I will clarify it with the help of the graph. So what do you see here? Let us say peak current. Okay. When I increase the, what do I mean here? Now let us try to understand this graph and try to get some conclusion from this graph. When I increase the current from 2 to 4 amperes, it has a profound effect on micro hardness. Micro hardness increases and it increases substantially. When I change current from 4 to 6, though micro hardness increases, but the effect is not significant. Similarly for this. Okay. When I change, now come to the second graph. When I change 5 microsecond to 10 microsecond, it has an adverse effect on micro hardness. Micro hardness goes down. Then again it further goes down when I go from 10 to 20. So I am able to find out the individual effect of the factors. Got it? I will quantify it also. Okay. Right now I am being able to get that effect. You see two lines here. One is representing SN data, one is representing raw data. This is just for clarity. When you actually use this method, you need not go for raw data. Okay. When I go to the second one, again that effect you can see, but you notice one difference, that SN data is going one way, raw data is going other way. Why? Because this characteristic is seeking the minimum value, whereas SN ratio always seeks the maximum value. Got it? Now, what is my further inference from this? It means that the highest value of current, please listen this thing carefully, highest value of current, whatever I used, lowest value of pulse on time, and highest value of pulse on time gives me the highest micro hardness. I am able to see the effect of all those three together. I use different levels. I studied the interaction, put them into a matrix. Now what is the result coming out is, if I want to maximize micro hardness, use current 6 ampere, use pulse on time 5 microsecond, use pulse of time 85 microsecond. You will get the best micro hardness. I have optimized further. Similar for surface roughness. We'll take it micro hardness. I think that will make you the things clear. Now, my optimum combination comes out to be 3-1-3, isn't it? A3, B1, C3. That is my optimum combination. My analysis tells me that the highest value I will obtain at A3, B1, C3. But did I use this combination in the array? Let's check. Did I use this combination 3-1-3 anywhere? No. Even though when I am not using that combination, Taguchi methodology is telling me what is the best combination. Okay. And it will also tell me I have obtained certain values. I have obtained certain values of micro hardness here. But it tells me that the best combination is not here. Best combination is somewhere else. And if you use that combination, what value you will get? Let me calculate. Optimum value of eta, m plus ma3 minus 1, mb1 minus mc3. So best value of A3, take the SN ratio for A3, take the SN ratio for B1, take the SN ratio for C3. And then I used a formula, log, and then now you reverse that formula. That is very simple. You get the optimum value. I have written here in red color, 682 Vickers hardness. So if you use this combination, you will get 682 micro hardness. Okay. Now what I need to do is, I need to conduct a confirmation experiment. Whether, now I will use 3-1-3. And it also tells me that this is my theoretical value. Once you conduct the experiment, how much, which range it should lie. So that range you can calculate. This is the confidence interval. This is the formula here. Okay. So F alpha, tabulated value of F ratio at 1 error degree of freedom. VE is the error variance that will come from the ANOVA table. Let me explain the concept. We will go to the ANOVA table. So using this, I calculated the confidence interval came out to be plus minus 0.9636. That means minus 0.9636 plus 0.9636 of the optimum value. Make that change, find out the raw value. So it must fall. Here he is saying the range he has given for the surface roughness. Range should fall between 2.08 to 2.57. That is when you conduct the confirmation experiment. This is the range in which that should lie. Okay. So we conducted the confirmation experiment. We found out to be 2.46, which is within the confidence interval. That is one. Then let us come to the, I'll spend 5 minutes on the ANOVA table also. Analysis of variance. Taguchi suggests two different routes to carry out the complete analysis of experimental data. We can, basically it means that we can do ANOVA on raw data also. We can do ANOVA on SN data also. But preferably we will do it on SN data. Okay. So I have done that. So this gives me, these are the factors I have taken: peak current, pulse on time, pulse off time, error. Okay. What is sum of squares? Sum of squares due to factor A. Value of SN ratio at A1 minus mean ratio. Value at A2, A3 minus, square them, multiply them 3, that is the sum of square due to factor A. Similarly, you will calculate sum of square for factor B, sum of square due to factor C. You will also calculate the total of sum of square. Total sum of squares, you take all SN ratios at the same time, that gives you the total sum of squares. Total sum of squares is equal to sum of the sum of squares due to the 3 factors plus the sum of square due to error. So you will get the sum of squares of error by this formula. You get this? This column is clear. Sum of squares column is clear. Degree of freedom I already told you. Variance is sum of square divided by degree of freedom. F ratio is variance of that factor divided by the error variance. Variance of that factor divided by the error variance. And if this F ratio comes more than the tabulated value of F ratio, which is available from the table, which just in the beginning I was showing you. So if that is more than that, the factor is significant. If it, in our case, this value is 19. So all these factors are significantly more than 19. So all these are significant factors. And then you can calculate the percentage contribution. Simple, sum of square of that factor divided by total sum of squares multiplied by 100. Okay. So you see now what ultimate analysis you get here is current is the most significant factor. 70% contribution. Pulse on time, 22% contribution. Pulse of time, 7.8. What relevance this information carries to an researcher? That even if I don't change pulse of time, my experiment is not going to be affected much. But if I change my peak current, suddenly my experiment will change drastically. And of course, pulse on time is also 22% is also a significant contribution. And error, as I told you, this is very less because this is not an actual experiment. So this is very less. Actual experiment may be 1%, 2%, something like that. If it is less than 5%, you can accept your results as satisfactory. Okay, these are the ANOVA calculations. F ratio for a factor, variance of that factor divided by error variance. Similarly, percentage contribution. So basically we don't need any software. What I'm emphasizing here is once that you have the conceptual knowledge, you can do it easily on an Excel sheet. Okay. sum of squares due to that factor, total sum of squares multiplied by 100. So let us summarize. We begin with, we wanted to find out optimum combination of the process parameters. We were able to find out. Best value of the response parameter, we were able to find out, even when the combination of the input parameters was not within that orthogonal array, isn't it? This is very relevant when we go in for higher arrays, like we are using L18 array or L27 array. This becomes very, very important because we are conducting only a fraction of experiment, but it is still able to tell me that what is your optimum combination and how much response characteristics value you will get if you conduct experiment on these values. Best value of response parameter, significance of the process parameters we are able to calculate. Even if one factor is not significant, ANOVA will tell me. Percentage contribution of the process parameters. So this also we have been able to find out. This L18, you can just practice on this. Later on you can do that. So I have given you that. Some values also I have given. This I have explained in detail, but can we take, sir, 5 more minutes? No problem. So quickly I will go through it. So dummy level, as I talked about, is in a 3-level column if you want to fit a 2-level factor. So we can do that. What we will do is, we will take one of them. Choice is, now actually we have 2 levels, A1 and A2. But in my array, we have 3 levels, A1, A2, A3. So our choice is A3, we can take A1 or A2. Okay, it depends on many factors. If A3 is taken as equal to A2, A2 is estimated with 2 times more precision, obviously, because we have taken twice that rows for that. If A1 is the starting condition, we have a fair amount of experience. A2 is a new alternative, you take A2. Whatever you consider more important. Like if I go back to the example I have taken, current came out to be very, very important. So I can take 6 levels of the current. So current will be estimated with the double the precision. So that is the basic idea of this technique. So this is what is mentioned here. I have again taken an L9 array. So last 3 you can take either 1, 1, 1 or you can take as 2, 2, 2. You can later on do some analysis on this. The orthogonality is still maintained, you will find. Orthogonality of the array is not disturbed. Second is the column merging method. That means you can merge 2 or more columns and conduct an experiment with much more levels of the factors than the array permits. So that is the column merging method. I will again briefly explain it. You see here, this is an L8 array. He has merged 3 columns, 1, 2, and 3. So by merging this, though earlier it was possible only to study 2 levels of a factor, now it is able to study 1, 1, 2, 2, 3, 3, and 4, 4. So now it is able to study 4 levels of a given factor by using a 2-level orthogonal array. So this is what is meant by the column merging method. So you can, this is very common in L18 because maybe some of you will be actually using it. So I want to emphasize, like in L18, first column is for 2 levels, second column is for 3 levels. So it is very common to merge these 2 columns and use them to conduct a 6-level factor experiment.
Those are significant even.
Those, and that is most significant because it is on the left side. It is most significant. So, and most significant, you would like to study at more levels, isn't it? So this is a very, very good array for conducting your experimentation, L18. Okay. And lastly, compound factor method. It allows us to study more factors with an orthogonal array than the number of columns in that array. Okay. For example, it can be used to assign two 2-level factors to a 3-level column. So otherwise a 3-level column will be used to study only one factor. Now we can assign 2 factors each with 2 levels. But as I told you earlier, this makes it complicated. I will briefly describe it. Suppose we have 2 factors with 2 levels. Total combinations are A1, B1, A2, B1, A1, B2, and A2, B2. You can eliminate either the last one or the first one. Suppose I eliminate the last one. I have 3 levels left. I can assign it to a 3-level column. Now change from A1 to A2 will be given by the first 2 levels. You see A1, A2, B1, B1. So B1 remains same. So change from A1 to A2 is given by the first 2 factors, and change from B1 to B2 is given by first and third, A1, B1 and A1, B2. So in that case, A1 remains same and B1 is changing from B1 to B2. Similarly, if you eliminate the first one, you take the last one, you will be able to study A2 to A1 from this and B1 to B2, B1 to B2 using first and third. Okay, just go through it. You will be able to understand it. So this is how the assignment, 2 factors have been assigned to a single column. I am using this now, this L9 orthogonal array to study 1, 2, 3, 4, 5 factors. Of course, 2 with 2 levels and 3 with 3 levels. So that is how it is done. But this last method is best avoided because it results in errors. So I conclude my talk here. Thank you very much for the patient hearing, and I hope you found it useful.